Okay. Now I request our President Professor Neelam Shrestha Pradhan to take chair for this session, NPS Monthly Talk Series today.
Yeah. Thank you and welcome all of you here.
Yeah. Thank you, ma'am. Thank you. Today we invite one of our life member outside from our country. It's really rare, Professor S.N. Pandey. Thank you, sir, for accepting our invitation. We are really fortunate to listen you today. Now I would like to request our Vice President, Dr. Leknath Mishra, to read out a brief CV of today's speaker, Professor Pandey. Leknath, sir.
Okay, thank you, Malik sir, Chairman. I would like to say something about Professor Dr. S.N. Pandey sir, who is very famous, and he did his PhD in 1992 on material science. He is an expert in both theoretical and experimental work. So now he has 9 PhD students. Out of them, 6 already done, and 3 are conducting PhD. And he has 2 postdoc students. And he is the reviewer of the reputed journals, international journals. He is the member of Nepal Physical Society, as Malik sir said. He is the visiting fellowship, and he has 2 projects. One is symmetry and integrability of certain non-linear dynamical system, and another one is investigation of chemical gas sensor based on low-cost thin film of metal oxides semiconductors. So he is going to deliver his speech. Thank you, sir.
Thank you, Leknath, sir. Professor Pandey, now the floor is yours. Could you please share your screen now? And great.
Yeah, that is yeah. Takes some time. Yeah.
Thank you.
So should I start, sir?
Sure. Yes.
Yeah. Okay. So नेपाल भौतिक समाज प्रति हार्दिक आभार प्रकट गर्दर छु. I take this opportunity. I am here to thank Nepal Physical Society for giving me this opportunity to share my recent findings. So especially I am thankful to Professor Neelam Shrestha, President of Nepal Physical Society, Professor Leknath Mishra, Vice President, and Professor Harishankar Malik, the Secretary of the Nepal Physical Society. It is worth mentioning that Professor Malik, I am very happy to see that he used to send mail in the morning, and I also uh, used to see this mail in the morning itself, and that's very good one, sir. This gives your dedication. This shows your dedication. So the topic of my talk is future energy storage devices, that is supercapacitor. So one can see that we should start. I have been told that I should concentrate for the student side. So some slides are there related with the students. So Louis Pasteur, that is given, science knows no country, because knowledge belongs to humanity and the torch which illuminates the world. So by the way, whatsoever written on right hand side, I am unable to see it. I have to just guess it because photographs are coming there. Anyway, but I can manage it, no problem. So let us call this one that Feynman has given this lecture in on December 29th, 1959, that initiative to enter a new field of the physics, and he has given the possibility of the direct manipulation of the individual atoms that is more powerful than synthetic chemistry that has been used at that time. So this is the talk, very interesting one, 1959 one can see, and after that nobody thought about that one, and in the beginning of 1980s the nanotechnology that came into picture, and the work has been started there. So here outline of my presentation is introduction to nano thin film energy storage, then supercapacitor. After that, specifically that we will come to the strontium hydroxide thin film as supercapacitor electrode. Then yttrium doped strontium hydroxide thin film for supercapacitor electrode. And lastly, that is fractal characterization of the supercapacitor. So this is my outline, and I'd like to summarize the each subpart. So see, nowadays we are talking about the energy environment economy, that is primary issue for the human development. And in general, the clean energy or inverter-free energy. So that is divided into three parts, that is harvesting from the renewable energy sources, conversion and storage. So all the three are having their own advantages and disadvantages. Here we will see about the energy storage, that is the supercapacitor. So as I have told you that this word nano is coming very frequently nowadays. So let us see that what is nano and the origin of this nano. So it comes from the Greek word nanos. It means that very small. So very small means how small, because in science and technology we have to give some measurement there. So on meter scale one can see that 1 billionth of the meter, that is 10 to the power -9 meter, it is there. So if you are going to that scale, then it is going to the nano scale. And nanomaterials, they are having many applications, not only in physics, chemistry, but in engineering, even in biology. We will see that number of applications nowadays in these fields. So what is happening that if you are going to nano scale, so one person is waiting there, Jagga Baral, he is waiting to enter, sir. Can you permit him?
We already permit, sir.
Okay, okay. So, okay. So you can see that if you are going to nano scale, then what is the changes that is occurring? So two things are occurring. Number first one is quantum confinement effect, and number second is the increase in the surface area to volume ratio. So when we are going to the nano scale, that is, size of the nanocrystal is smaller than de Broglie wave, then electrons are and holes. So what is happening? They are especially confined and electric dipoles are formed. So once the electric dipoles are formed, the energy levels becomes discrete. So it is similar to a particle in a box. So energy separation between the two adjacent levels, that is changing if you decrease the dimension. So due to this one, we are having the unique optical and electrical properties of the nanomaterials. So one can see here that if it is the bulk one, bulk crystal, then energy gap, we are having this band gap and a thin film. And as you are increasing the dimension, one can see that how these energy levels are changing. So here that one can see the discrete energy levels. So there are the discrete energy levels, and due to change in the energy levels, it is having the significant change in the property of the material from the bulk. So this is the basic phenomena which is happening there. And moreover, one can see here that if volume to surface to volume ratio, it is also increasing. So if you go to the nano scale, then one can see that the volume, it is the remaining the same one, but surface area is increasing. So that is very important one, surface area. All the phenomena are the surface phenomena. So that's why we are getting change in the application side. So this is giving very good uh, idea that how one can see its application. So since my work is related with the supercapacitor, so I should introduce briefly that what is the capacitor. It is well known that is two passive two terminal device, and one can see this is structure of the capacitor. So capacity of the supercapacitor, it is given like this one, epsilon A by D. So if you want to increase the capacity, then one can see that if you change this area and decrease this D, then this capacity it is going to increase. So one can see that what is happening here. So if you compare the parameters, basically that we are having the energy storage devices, capacitor and battery. In case of the capacitor, one can see that is power delivered here is the rapid discharge, linear or the exponential voltage decrease here. And energy density is, it is very low one. Energy density, it is very low one. In case of the battery, one can see that energy storage, it is very high, and energy density, it is very high, but power density, it is low one. So one can see that power density, it is very low. So it is the supercapacitor which is bridging these two, that is capacitor and the battery. It is having the beauty of these, that is capacitor and the battery. So its energy density is also high, power density is also high. Moreover, one can see its operating temperature. So operating temperature, that is also minus 40 to 85 degrees centigrade. One can see that is the supercapacitor. That's why scientists are working for the supercapacitor in this area of the supercapacitor, that is to store the energy. It is very important to state here that generation of energy is very important one. But once the energy has been generated, so storage, the second thing is coming as a storage. How will you store the energy? Because if you are not storing the energy, then we cannot use it later on. So one can see that beginning of the supercapacitor, it has been started in 1950 by electrical engineer. They have started it, that porous carbon electrode they have used for the fuel cell and rechargeable battery. So it is Baker, H. Baker in 1957. He has developed this low voltage electrolyte capacitor with carbon electrode here and given this name, that is supercapacitor or ultra capacitor. So it is storing energy in a better way. So one can see it here. So basic design of the electric double layer supercapacitor EDLC type, that one can see that porous electrode are there, and they are the electrolyte, and we are having this double layer here. So one can see it what is happening, that is two electrodes are there separated by here, that is a separator is here which is separating these two, and two types of the ions are that is being produced in the solution. So conventional thing, that is we are familiar with all this. So if you want to divide the supercapacitor, then there are the two main categories, that is Faradic and non-Faradic. So in case of the Faradic, so what is there? That oxidation and reduction process that taking place. So, but that is governed by the Faraday's law. So if it is governed by the Faraday's law, then that will be Faradic. Otherwise, it is going to be the non-Faradic. In Faradic behavior, we are having the pseudo-capacitive behavior, battery type behavior, and in non-Faradic, we are having the EDLC type, that electric double layer capacitor. It is of two type here, that is activated carbon, graphene, carbon nanotubes, etc. So one can use. Further, one can see that here. So this can be divided into two parts, that is pseudo-capacitive behavior and battery type behavior. And combining these two, we are having pseudo-capacitive battery type behavior. So it is bridging this gap here, that is pseudo-capacitive battery type behavior. So some of the capacitors which we have developed, it is having the pseudo-capacitive battery type behavior. So one can see here, that is what is that capacitor, that is energy density, power density, that is Usain Bolt is here, who is having this 200 meter or 100-meter race. So power density, that should be very high, but here for the marathon, energy density should be very high. So prototype Shanghai supercapacitor electric bus that has been operated by China, and its cost one can see in Indian rupees, it is 62,000. But for the supercapacitor, maximum speed is 45 kilometer per hour. Capacity is given here, and once it is charged, then it can travel up to the distance of 5 to 9 kilometer, and then we have to charge it. So a lot of works are going on, just how to reduce the charging time and increase the distance. So all these things are possible if you have the capacity is high one. Capacity, that one has to increase this capacity. So it is having many applications, that is super capacitor bank here. Once it is charged, then it is bank, and it can be used in many ways. So advantage of the supercapacitor, that high energy storage and working temperature one can see, eco-friendly, quick charging time, maximum life cycle, high efficiency, and so on. So these are the some advantages. If there are some advantages, then there are the disadvantages also. So one can see the disadvantages. So energy density, that is slightly low one. Then if you compare with the battery, the voltage varies with the energy stored. If energy stored is more, then voltage that will be more. Have high self-discharge rate, and so on. So these are the some negative disadvantage of the supercapacitor. So my work is related with the thin film. So I thought that I should introduce briefly that what is the thin film, what does it mean. So thin film is a thin layer of the material with the over the substrate. Substrate means that is over on which we are depositing that one. So one can see here that this is the substrate and the thin film that has been deposited here. So there are different types of the thin films. On the scale one can see here that we can call up to this scale, that is the thin film, then thick film, and so on. So researches are going on the thick film also. It is having also some applications. So classification of the thin film, that is of the 4 types: single crystal, epitaxial, monocrystalline, amorphous. So these type of the thin films are there. And see that very easy method that we have used, successive ionic layer absorption and reaction. So what we do, we take the 4 beakers and brief, it is called the Silar method. So we dip here, the substrate is here, we dip here in this one solution, then in DI water, then here anionic, then cationic solution, that is we are dipping it here, then again here the DI water, and after that this layer, it is being formed. So what is happening in between these two, we are having this water, DI water. DI water is used to remove the loosely bound atoms. So loosely bound atoms that is being pulled out here. So optimization is very important one. How many layers that is needed, and timing of dipping the substrate in anionic and cationic solution. That is also very important one. We have to optimize it depending on the situation that we should optimize. So one can see here. Further, we have extended it to LBL, that is layer by layer method. So we tried to form composite. So composite, that is one layer, for example, strontium hydroxide, then another composite here, that is 4 beakers we have taken. So it is going to be layer by layer, one layer of this one, then another layer of that one. So in this way that we can form the composite. So that's why it is called the layer by layer method, that is extended form of the CLR one. So one can see that's advantage and disadvantages of the CLR. So it is having this advantages and disadvantages. So verily one can see that it is a very useful one. So now come to the strontium hydroxide thin film as supercapacitive electrode. So very first time that we have tried this strontium hydroxide for the supercapacitive electrode. So what we do, see that this video that was not working, that's why I have changed that to the other laptop, but unable to have the audio system, but their audio system was not working. So that's why, otherwise this is a very good video to show you. See, one can see it. See that it is not possible to show you. So it is dipping in the first one, then it is absorbing here atoms of the strontium, then you are dipping this Di water. So it is the Di water, then loosely bound atoms, they are coming down. Then here, that is not hydroxide. So in this way, that is a one layer it is being formed. So that was showing very good video. It was not working by the way. It is not working here. So one can see that is SS substrate is here. Then strontium, it is being absorbed. Then we dip in the Di water. Then either sodium hydroxide is here. So it is reacting with the sodium hydroxide. So strontium hydroxide finally it is being formed. So I wanted to show this video. It is not, by the way, it is not working. So finally that we are having this strontium hydroxide that is being deposited. So this is the schematic diagram of the deposition of the strontium hydroxide thin film. So one can see that once it has been deposited, then as I have told you earlier that we have to optimize the number of the time here, that time, how much time that we have to dip in these two solutions, number first, and number second, that number of the cycles. So one can start from the 10 number of the cycles, then 15, then 20, or one can go to the 5 also, that is possible, and try to see that which one is giving the better result. So one can see here that deposition that has been completed, then the second thing is going to be characterization. So characterization is very important one. So how can we characterize it? So one can see that XRD pattern, that we should see the XRD pattern. And nowadays it is very easy to analyze it with the help of JCPDS card. So we are having the different SS here. It is denoting the peak due to stainless steel, which is this substrate one. So I have taken the stainless steel as the substrate. So this is small peaks are coming due to this one. This is also due to the stainless steel. It is written here. And strontium hydroxide, it is having this peak. So one can see that one peak is 26 point here 25 and 26.9 degree corresponding to 011 plane, and 26.36 point here 36.2 corresponding to 400, and 45 point one can see that this 45 point, yeah, this one, this is having the 411 plane and so on. So all that we have analyzed it, and they correspond to the orthorhombic phase of the strontium hydroxide. We have calculated the crystallite size by using Serrer formula, and we have obtained that D, it comes out to be equal to 3.52 angstrom, and the value of A as 9.606, value of B as 6.129, and value of C as 4.309 angstrom. So all the units are the angstrom one. Then further we have analyzed this FTIR, that is Fourier transform infrared spectroscopy, to know the chemical bonds present there. So it is taken from 4,400 centimeter inverse. We get the fingerprint of the IR spectra that 500 to 1500 angstrom. So one can see that is different peaks here. By the way, that I cannot see, but I can guess that some peaks are here right hand side, corresponding to 439, that is stretching mode of the OSRO. Then HSROS, that is 498, and bending vibration of the water molecule at 1439, and stretching vibration of the physically absorbed OH bond, it is there from 3300 to 3800 centimeter inverse. And there is one more peak that is at 853. So one can see this peak corresponds to the some contamination of the carbon at the surface, because we are performing the experiment in the open atmosphere. So some contamination of the carbon that also takes place. So this is the FTIR. Then we can come to the SEM. SEM analysis is also very important one to see the surface. So one can see this surface morphology. So FESM image of the tuberose. So very beautiful structure it is having, that tuberose morphology. It exhibit high porosity. One can see that porosity is also very important aspect. So high porosity, as it consists of the secondary, ternary, and even higher order branches. So one can see that is the secondary, ternary, and higher order branches from this one that is here. So that's why porosity is going to increase. So if it is more porous, then it is giving the electrolyte to move inside, so to react it. So it will lead to the higher specific capacity. And insert here this shows, one can see that is chemical composition of the compound which are analyzed by the CDS, strong peaks of the strontium and oxygen. So one can see that is strontium and oxygen. So this guarantee that whatsoever that we have deposited, it is deposited here, and we get very good porous structure. So we hope that it will exhibit the supercapacitive property. So let us go to the HR SEM. So HR SEM, that is HR SEM and TEM images. So one can see here that very beautiful picture. So this figure B, it is showing the lattice fringes with interplanar spacing. So spacing coming as 0.33 nanometer. That correspond to the 011 plane of the strontium hydroxide, exhibiting the orthorhombic crystal structure. So whatever information we are getting, it is corresponding to the XRD analysis there. Then we have to do this now come to the application side here also, that one can see that TDS pattern here also strontium is present, oxygen is present. So we are interested in that one, since this sodium their carbon is also there. So it is possible that their carbon is also coming in this analysis. So already reported there. So characterization part, synthesis and characterization, that has been done, and we expect that it should give the supercapacitive property. So we should go for the electrochemical analysis. So for that one can see that we are having this cyclic voltammetry, CV curve of the strontium hydroxide thin film for the different here cycle. So we have to optimize the number of the cycles, that is 10, 20 and 30. So we have to see that which number of the cycles of the deposited strontium hydroxide it is giving the more area. So one can see that 20 cycle it is giving this more area. This is the 10 cycle, black color, and this one, that green, it is the 31, but here one can see that it is giving the 20 cycle, it is better one. It is best one I can see here in this case. So a natural question that will arise that if you are going from 10 to 20, then surface area it is increasing. Then from 20 to 30, then why the surface area is decreasing? Then what is happening? Agglomeration process is taking place. It is mixing together. So that's why the surface area is decreasing, and due to that one, the CV, that is value here, that is decreasing. So we have to optimize for the different electrolytes. So one can see here that is the same color that has been used here. NOS is giving you the best result. So we have optimized it, the number of the cycle and the electrolyte. So a lot of researches are going on to take a particular material and to see that in which electrolyte it is giving the best result. So here that we have analyzed, that is NOS, it is giving the best result. So number of cycle is 20 and NOS is there. So we have to go here. So CV of the various scan rate, 1 mole NOS we have taken, and at various scan rate that we have plot here current and the potential. So here we will see that we are getting the best result for the 5-1, that is 5 scan rate, 5 millivolt per second scan rate. So we are getting here this maximum value. So specific capacity comes out to be equal to more than 300. So it is 308 coulomb per gram at 5 millivolt per second scan rate. If you are increasing the scan rate, then the specific capacity is decreasing. Scan rate means that is electrolyte is getting, it is getting more time to interact with the electrolyte and electrode. So that's why we are getting here the maximum value. As we are decreasing, then less time is there. So that's why this specific capacity is decreasing. So one has to optimize and one has to calculate. So we have used this formula to calculate the specific capacity, and its value comes out to be equal to 308 coulomb per gram, and at this scan rate is there. So there is another way also to analyze it, that is your charge discharge method. So with the help of this charge discharge method also, that we have optimized it and tried to analyze its specific, obtain the specific capacity. So one can see that is constant current charge discharge curve of the transformer at the various current rates. So current rate that is given here. So we are getting the maximum value here at this E. E is going to be 2 milliampere. So that is maximum one, and here 1.5, that is in between, and C that is less one. And capacity, then one has to see that if you want to use as a capacitor, then the find out the capacitance retention with the number of the cycles. So we have analyzed up to 5,000 number of the cycles here, that is 5,000 times the charge and discharge. Then one can see that up to the here, up to 500 or so, its capacity that is decreasing to the 51, and then up to 5,000 it is retaining to more than 35 or 30, more than 31. So more than 30% of the capacitance that is being retained. So this can be used for the supercapacitor application. So further that we have done here this Nyquist plot. So Nyquist plot. So here one can see that we have the fitted with this one, and this is actually, and we have obtained it equivalent circuit is given by this one. So from this equivalent circuit, we have calculated the value of RS and RCT. RCT is charge transfer resistance, and in this case, charge transfer resistance comes out to be equal to 3.78, and RS see the solution resistance, that is 1.52 ohm per centimeter square. So for a better supercapacitor application, the value of the RS and RCT, that should be small one. So here it is comparable one, so one can see. So if you summarize it, this part, then we will come to this conclusion that it is having the specific capacity as 413 coulomb per gram. So this is the first report on the strontium hydroxide. So once we have concluded that this can be used at the as a supercapacitor, then next task, that how to increase the specific capacity of the strontium hydroxide. So there are the two ways. Number first one, that one can try for the doping of the other material. So we started doping it, and different dopings that we have done it, and one can do for the composite also. So that side by side that we have done both the things. So doping, so we doped with the copper, we doped with iron, then the yttrium and so on. So to increase the specific capacity of the this strontium hydroxide, first one. And second thing, that we try to make the device, because we have to make the device so that one can use it practically. So for that, one can see that the next part, it is going to be wide doped strontium, yttrium doped strontium dioxide thin film as a supercapacitor electrode. So this is the supercapacitor electrode. So how we increase, the aim is to increase the specific capacity of the supercapacitor. So same method that is we have to use. So we have used the same method here. That is, precursor we have taken strontium nitrate and yttrium nitrate. So this is the precursor, and we have optimized it for the 20-second, same CILAR method that is we have to use, and NaOH is here. So with the help of this one, we can make the strontium yttrium doped strontium hydroxide thin film. So this is the symbol for writing the yttrium doped strontium. There are many ways that one can write it. So here that we have optimized the time and then prepared this one, and this is the schematic diagram. So one can see that once it has been synthesized, the method is same one, that is the CILAR one. Then we have to characterize it. So for the characterization, one can see that is the XRD. First of all, with that we should take the XRD. So in case of the XRD, we are having this undoped, and then doping here, that is 5%, 1 atomic percent, 2 atomic percent, 3 atomic percent, and no, it is 0.5. 0.5, there it is going to be 1 per atomic percent. This is 1.5 atomic percent, and so on. So in this way, that is, we have tried to increase this atomic percent doping and try to see this XRD. So in the XRD, that we will see that is no extra peak that has been obtained. One can see here that is no extra peak that has been obtained. Moreover, the shifting is taking place. One can see this is the shifting. So no extra peak means no phase of any other compound or the material has been developed. It means that doping does not change the crystal structure. So crystal structure that is remaining the same one. And there is a change here. That is, as you are doping here, then the nature one can also see that whatever in case of the previous one, that short peaks were there, but the peaks nature that is also going to decrease here. That peaks are decreasing. It has been observed that amorphous nature is giving the better supercapacitor behavior than the crystalline one. So it is moving towards that one, and so on. So here that is very good. XRD is needed to exactly see this statement, but roughly that one can see whatever that we have observed. So now this come to this FTIR. So FTIR one can see that is 701 centimeter inverse for the undoped strontium hydroxide. So undoped is there, and it is, this peak is shifting to the left side, which is known as, indicates that the red shifting it is taking place. So why this red shifting is taking place? Because due to the creation of the defect as a result of the white doping. So if you are doping the yttrium with the strontium hydroxide, so it will create some defect. So as we are increasing this atomic percentage, the defect that is going to increase it. So YSR2 shows the most intense peak, that is maximum number of defects it is there. So if the maximum number of defects are there, it means that that will be more suitable for the supercapacitor, or its a specific capacity that will be more. So one can see that 854, it is corresponding to 854. This corresponds to the 54 in carbon contamination, and 41439 corresponding to that one, that is the water molecule, and physically absorbed, that is OH bond, it is there to 3300 to 3800. So that is there, it is here right hand side. So FTIR, that is we are slightly getting the, we are getting the information that yttrium has been doped here, because that shifting is taking place, it is creating the defect. So after this one, we have to go this FECM image. So FECM image, that is very good tube rose structure is there, and apart from the tube rose, one can see that something more, that is nanorods like a structure with the tube rose. Nanorods, one can see here, nanorods like a structure with the tube rose, and it is mainly due to the Oswald ripening process, that is some terminology had been used, and its orientation mechanism. So one can see that nanorods, it is pops up over the tube rose. Tube rose, one can see here that whatever is shown here in this circle, that has been enlarged to right hand side, and one can see leading to the increase in the surface area. So what is there, whatsoever the surfaces that that has been developed, it is growing in the some other direction, in the popping up in the some other direction. So it means that it is increasing the surface area. That is very beauty here. So one can see that is with the help of the yttrium doping, it is increasing it. And as we increase the atomic percentage of the yttrium in doping, then what we will obtain, that is agglomeration of the rods increases. So they are going to mix together. So that's why the surface area, it is not increasing one. So one can see this index also, index that will show you that yttrium has been doped. So this is the index. So in this index, we are having this yttrium, strontium is there, oxygen is there, and so on. So this shows that yttrium that has been doped in this strontium hydroxide. So after getting all the characterization, now we should go for the chemical analysis, electrochemical analysis of this one. So this is the CV curve of the yttrium doped strontium hydroxide. So I have written here YSR 1, 2, 3, 4, just to differentiate all the 4 samples, and that we have calculated the specific capacitance and its value that has been written here. Then we should go for the charge discharge. So charge discharge also that we have shown, and maximum value that is written here. I am unable to see it, but one can find it out that what is the maximum value. It is something that will be given there in the conclusion part. So here, that is see, it is very GCD curve at 0.4 milliampere. So Faradic region, that is here charging and then discharging. So this is the IR drop, and then Faradic region that is being observed. After that, we should have we have to find out the capacitance retention. So here gone up to the 1000 number of the cycles, and retention, it is coming more than 75, more than 70, more than 70%, that is capacitance retention is there. So then we have other characterization, that is the Nyquist plot of this one. So Nyquist plot of charge discharge, another thing that has been observed. So here also, that is whatever solution resistance and other thing, that is coming very low. So this shows that this will have the better property. Then one has to make the device, as I have stated earlier, that how we should make the device. So this is the actual photograph of the device which we have made. So this is one uh, symmetric device. Symmetric means that is both the electrodes are of the same material. So that one electrode that has been deposited here, that yttrium dot strontium hydroxide, this is the another one. Then we have joined it together, that is here, that is there some procedure. So with the help of that procedure, we have combined it together. In between there is some gel in between, and then we have packed it and put here some weight for overnight. Now this device, it is ready to use for the practical application. So one can see that is the how that one can use it. So for that one can see it here. So the device also, that we have to characterize the device for this CV and other things. So that has been done here, that is electrochemical performance of the solid state symmetric electrode device in that gel Na2SO4 gel electrolyte with different potential window. So one can see that potential window 0.5 volt to 1.5 volt. So that is a very good result. It is giving that this device can be used within this potential range. Then one can see here that with the help of charge discharge also, that we have calculated. And this is very interesting slide, that is giving the actual application of the yttrium dot strontium hydroxide. Here that we have made two devices and then connect it together, and then we have to charge it. So this is the charging process. After it is fully charged, then we have to discharge it. So we have to discharge with different LEDs. So one can see that illumination of the LED after this 3 seconds, 17 seconds, 31 second, 50 second. This is the LED which is glowing. This is the LED which is glowing. This is also the LED which is glowing. So this shows that practical application of the device made here. So what we conclude, that is we can make a device with the help of this one, and this is having the very good potential window, that is from 0.5 to 1.5 volt. So let us see that further this cycle retention of the symmetric device for the 1000 number of the cycles that we have seen. So it is more than 51 for the 1000 cycle, and this is the last retention one cycle. And then we are having this Rogan plot, that is B. So it is the supercapacitor region, and we can see here that a specific energy, and this is the specific power. So it is coming here. So that's giving very good result, that one can make use this one as a device. So let us conclude this part, that is we are having this wide doped strontium hydroxide electrode by Szilard method, and we get here, that is a very good picture, that is FECM, that is some nanorods like its structure on the tube rose from morphology there, and prototype symmetric supercapacitor, that is electrode that has been assembled. And this device, it is having this rating, that is 31.8 and whatever 18 farad per gram probably. And here the specific energy that is given, a specific power that is also given here. So one can see that in this way that we can use the yttrium doped strontium hydroxide as a device. As I have stated earlier, that we have done some more dopings, that is copper, iron, and so on, and then composite we have made. So very quickly that I can show you here composite. There's some other composite that is there. So this is also composite there. In this case also that we have made this device and so on. So that is also that some other composite that we have made. This is also giving very good result. So these are the some works that has been done on the application side. This is also one can see the different LEDs that has been glown with the help of this developed one. It is symmetric device. Symmetric means both the electrodes are same. It is both electrodes are different. Then that is going to be the asymmetric device that is there. So this is all about the experimental work that we have done. And then while talking with the group there, we started the fractal characterization of the thin film supercapacitor, and that Leela Pradhan, she has given some input there, and we have started. We are trying to start or started slightly with the Neelam Sest also. That is on some other problem. So let us see. This is the theoretical part. That is, what is this fractal? So fractal word that has been coined in mathematics. An object or a mathematical set with a self-similar pattern is called fractal. So a very good example of this one is the cauliflower, and the right hand side one can see that is the fractal. I should repeat once again that this word has been used in mathematics, first of all, and then it is having application in many areas. So we have also used this idea to identify, to analyze this one supercapacitor behavior. So one can see that is the fractal one. So fractal study, what is that one? A fractal is an object or quantity. It displays self-similarity in somewhat technical sense and so on. So there are the self-affine and self-similar. If suppose that it is the scale, if you go to the enlarge in the different direction by the same scale and same pattern it is formed, then that is called the self-similar one. And in different scales, if you are changing the scale here, then also that same type of the structure that is called the self-affine. So self-affine and self-similar type the structure is there in the fractal. So this is the some definition part. Now come here, that fractal analysis. So classically that we were using this parameter that interface with W and average roughness or the global characterization of the roughness, but it miss out the important characteristic of the surface profile. So what is happening on the surface? It is missing that one. One can see here that two cases are there. If suppose that your probe, it is having larger than this one, then it will obtain this type of the structure, and it is very narrow also, then also it is not suitable one. Then with the help of the interface width and average roughness are only the sensitive to the peak values of the surface profile. Since my samples are the thin films, so in thin films, so if you want to calculate the interface width and average roughness, then it is sensitive to the peak value, that is peak value of the thin film, but it is not giving the idea about the irregularity or complexity of the surface. So fractal analysis can provide richer characterization of the surface morphology, and it is a scale independent property. That is very important one. So one can see that there are the many methods to analyze the surface. So here we are using the Heizuki algorithm. So what is this algorithm? It is easy technique for calculating the fractal dimension or the vertical section of the surface from the discretized height data. So if we take the same images, then we discretize it. So the height of the vertical section can be denoted at x1, x2, xn, and algorithm sequence that one can form like this one. Then length, LMK of the segment, it is given by this one. So this is the mathematical derivation of that one. So basically, one can skip this part time being, then try to see that what is the result. So basically that we get here that Lk, it is k raised to the power minus df, where df is the Higuchi fractal dimension. So this is the fractal dimension that one can obtain. And once the fractal dimension it is obtained, then we can calculate the Hertz exponent. Hertz exponent is equal to 2 minus df. So it is the fractal dimension df, it is going to give you the fractal dimension, but it is not always the integer one. It can have any value. So 2 minus df, it is going to give you s. So this is, shows that h and df, they are opposite to each other. So we applied it to the FECM image of the copper doped strontium hydroxide, and the graph of the log of Lk versus K, we have to find it out that which type of the curve that we are getting. So what we have done, we have discretized it and obtained that value, put it there. Then we have plot this curve. If this curve, it is a straight line, log Lk versus log K, then this shows that it is having the fractal character. Otherwise, it is not having the fractal character. So this shows that copper dot with strontium hydroxide, it is showing the fractal behavior. Then we have to calculate this fractal one. So one can see that fractal dimension here and number of the pixels. So one has to, that has been calculated. And Hertz exponent just opposite to that one. See here that fractal dimension is highest value. At the same time, one can see this is 2 minus df, so it is having the lowest value. So we applied it and we obtained for our sample, one can see that is the 1 atomic percent, 2 atomic percent, 3 atomic percent. And it has been observed experimentally that 3 atomic percent of the copper doped strontium hydroxide, that is having the highest value. So here also that we are getting this fractal dimension highest one. So this is the comparison and so on for that, and one can see it here. So this is the copper dot, and can you see here that is the value of the specific capacity that has been related with the fractal dimension. So for the different value that we are having this value of the specific capacity. So we have applied this fractal dimension to iron doped strontium hydroxide. So the samples that has been denoted by FS1, that is iron doped strontium hydroxide, FS1, FS2, FS3 for the different atomic doping. Here also that we are getting this a straight line. So this shows that it is having the fractal character. So we have calculated its fractal dimension, and one can see that FS2, it is having the highest fractal value of the fractal dimension. So correspondingly, its specific capacity thus is also going to be high one. So here we are getting that specific capacity that is going to be very high. Oh, I am running out of the time. I think I am watching only the Indian time. It is going to be 8 o'clock, but
Yeah. Yes, sir.
so this is the conclusion part that we are having, that fractal analysis providing, that is the supercapacitor electrode. So as I've been told that I should say something for the students. So for the student, I should quote here that I know I am something because God does not create garbage. So one should believe in this one and try to see it here, that one should just 1 minute. We should believe in ourselves, and here young person, they can have easily get the new idea. I can give the example of the Louis de Broglie. So sorry. Yeah. So Louis de Broglie, that in 1924 he proposed in his doctoral thesis the concept of the matter wave. He was a student at that time, and in 1926 Schrodinger waived this idea and developed the Schrodinger wave equation. In 1927, the existence of the de Broglie wave that was confirmed by the Davison and Germer in US, and the same conclusion that has been drawn by G.P. Thomson in England. But this experiment is known by the name of the Davison and Germer. In 1929, that de Broglie received the Nobel Prize of the Physics. And it is interesting to note that de Broglie was basically a student of history. So a student of history, he has developed the interest in the physics and got the Nobel Prize of the Physics. And it is also important to emphasize that why this experiment is known by Davison Germer and not by the G.P. Thomson, because they have reported earlier. So one should also take care of that one, that if you are getting some new results, then we have to report earlier. If you are not reporting it earlier, then that will not be very much useful. Now come here, that research, that should be your passion, and select topic of your research, whatever that you want, and try to work hard to achieve your goal. There is no substitute for hard work. One can see it here. And there is no magic which can make wonders over the night. So there are so many constants. Everywhere there are the constants. If you see my biodata, then I have started my research from the theory one, that is nonlinear dynamics. Then I have taken this challenge because supercapacitor that was coming up. So let us start it. So for starting a research work, one should have a very sophisticated lab and accreditation facility and so on. But I thought that what is the easiest way? That is, I started with the 4 beaker Silar method, and manually that we have dipped it for the 10 second, 20 second, 50 second, and so on, and we have optimized it. And in this way that we are successful to deposit it, then we have made the device also, and many composites that we have made. So now whatever the facilities available, that utilize the available facilities. Nowadays, many facilities are accreditation facilities are available, so you can do that one. And finally, try to do something for the upliftment of the human being. That is very important one. Wherever we are and whatsoever that our work is there, that should be for the human being. So I should stop here, and thank you very much. Neelam, probably that you are slightly tired. Yeah.
Thank you, Professor Pandey. Thank you very much. Now, I would like to ask our viewer to ask question. There is one question already in our chat box. May I read it, sir?
Oh, so okay. So that I can also see that here one question is there. Kesav Pandey from the Daegu University, South Korea. Oh, that's very good one. I have one question. Most of the supercapacitor devices have been tested more than 1000, for example, like 5000 cycles. What could be expected? This retention and coulombic efficiency from. See that if you increase the number of the cycles, then definitely the capacity retention that is going to decrease it. So better supercapacitor or device is that one which can retain the capacity for a longer number of the cycles. Nowadays, people are working for the 20,000 cycles and so on, just to show that this is the very good supercapacitor or the device they have developed. So one can explore in this way that there are the many limitations there. So if your device that is working very good one, so that will retain up to the 5000 or the 10,000 number of the cycles. So initially that we are having some limitations, we cannot go beyond 1000 cycle and so on. Now we can go for the higher number of the cycle. So we have analyzed up to the 10,000, somewhere into up to the 15,000, depending on the material. Whatever the device you are making, that should be capable to retain the capacity that is more than 50%, that will be better one up to the 10,000 cycle or 20,000 cycle and so on. Yeah. So chat box, there was one question that I have taken it. And if anyone is interested to collaborate, that I invite all of you. that if possible, then we can have the collaborative work, and we can collaborate on the experimental side, on theoretical side also.
Okay, one question. Can we have your email address?
Yeah,
So-
email that already that I have. Yeah,
Yeah, I have. I can share with.
yeah. Just I can share it. That will be better question that we have asked. Yeah.
Pandey sir, good evening.
Good evening, sir. Good evening.
Yes, I who was requesting for email address. I will email you for collaboration.
Yeah, email
we
is here. Email is given there.
Okay,
That
sir.
is one is institute email ID, snp@mnit.ac.in, snpandey12@gmail.com.
And we are also working on the same field.
Yeah, very good, sir.
Using,
Very good. Very
using
good.
bi-waste as supercapacitors.
Yeah. You are most welcome, sir. You are most welcome, sir.
So I will contact you, sir. I will contact you.
Yeah, we have collaborated with Professor Shankar Shrestha, Leela
Okay,
Pradhan. Nowadays that we are working with Neelam Shrestha also on one problem that is going on. Yeah.
So, okay, sir.
Thank you, Professor Pandey. We are running out of time. So I would like to Professor Neelam Shrestha to conclude the session.
Thank you very much, Professor Pandey. So we wholeheartedly thank for your very interesting and informative and recent year work. And most of the students I've seen, they are very much interested, and they are started some of the work with Leela Pradhan and Shankar, as you told. And in the near future, we also hope to see you very soon. And for
Yeah.
this note,
Yeah.
we'd like to conclude the talk series of Nepal Physical Society for this February month. And for March, we have another speaker. So thank you once again. Thank you so much, and thank you very much. Okay.
Yeah.
And namaste. As you said in Nepali, we are very grateful and thankful to you. धेरै धन्यवाद छ है पाण्डे sir. You wanted to talk in Nepali, so I said धेरै धन्यवाद छ, एकदमै राम्रो talk है.
So yeah.
Now we have Bhadra Pokhrel sir, Professor Bhadra Pokhrel sir. He is also working on supercapacitor. So please put few words, Bhadra sir. Oh, sir, your
Can you stop recording so that
okay.
informally that we can talk to